Welcome back to AI Paper Podcasts. You know, we all love ensembles for getting that extra accuracy and those really good predictions. Well, get ready, because today we're going to take a deep dive into a paper that kind of changes the game for how we use ensembles with deep learning.
Yeah, so what's super interesting about this paper is it looks at how just averaging predictions from a bunch of different models isn't always the best way to go. That's usually what people do, ensemble averaging, but it treats every model as if it's equally good, which we all know isn't really true.
So it's like if you're asking your friends for recommendations for a restaurant, but one of your friends only ever eats pizza, so their opinion might not be so helpful if you want sushi.
Totally. And that's where this paper comes in. They introduce a method called Soft Dawid Skene, or SDS, and it basically solves this problem. So instead of just averaging everything together, it figures out which model to trust more based on what you're actually trying to predict. It's like having these experts in your ensemble, and SDS is figuring out, okay, who do I trust the most for this specific thing?
So SDS is kind of like a judge then, weighing up each model's strengths and weaknesses to make sure we're getting the best possible prediction.
Exactly. And the way it does this is by estimating something called the confusion matrix for each model. This basically tells us how often a model gets each class right or wrong. So it gives us a good idea of how good that model is for each specific thing it's trying to predict.
Okay, wait, now I'm a little confused. Usually you need labeled data to figure out the confusion matrix, but don't we not always have that? So how does SDS do this without those labels?
Well, that's the cool part about SDS. It uses something called soft labels, which are basically the probabilities that each model predicts for each class. It uses those to figure out the confusion matrices without needing the actual true labels. It's kind of like a detective using clues to solve a case without knowing who the culprit is for sure yet.
Wow, that's getting really interesting. So it's almost like crowdsourcing, but instead of having a bunch of people giving their opinions, we have a bunch of neural networks, and SDS is figuring out which one's the most reliable for a certain task.
Yeah, that's a really good way to think about it. And it's especially useful when we're dealing with data that's different from what the models were trained on. That's called out-of-distribution data, and SDS is actually really good at handling those situations.
Okay, so not only is SDS helping to make our predictions more accurate, but it's also making them more robust, especially when our models encounter something new.
Exactly. And that means we get better calibrated predictions too. So we have a much better idea of how confident the model actually is in its prediction, which is super important when you're using these models in real-world situations.
I'm really impressed so far, but I'm also curious, how does SDS actually work under the hood? What's the math behind it all?
Well, math is actually quite elegant. They use something called a Dirichlet distribution, which is basically a way to represent how the probabilities from each model are spread out across the different classes.
So we have these probabilities, but how do we actually refine them and make sure they're getting better over time?
That's where the EM algorithm comes in. They use the expectation maximization algorithm, but with a really cool trick called Polyak averaging. That makes the learning process much smoother and more stable.
So it's like smoothing out the learning curve so the algorithm doesn't get stuck in weird places.
Yeah, exactly. And they even use something called automatic differentiation in one of the steps, which means they can use some of the really powerful tools from deep learning to update those confusion matrices we talked about.
Wow, it's pretty amazing how they've combined these ideas from deep learning and statistics to create this really powerful method. But before we get too lost in the details, I want to bring it back to our viewers. Why should they care about SDS? Why is this important for them?
Because SDS offers a real solution to a common problem in ensemble learning. It lets us use all the information hidden inside each model's predictions to get both more accurate and better calibrated results. And it's especially useful when we're dealing with data that's different from what the models were originally trained on.
So if you're out there working with ensembles, SDS is something you need to check out. It can help you squeeze out that extra performance and make your models much more reliable in real-world situations.
Totally. And now I think we're ready to dive into the experiments. Let's see how SDS actually performs when we test it out on different data sets and challenges. All right, so welcome back. Let's jump right into seeing how Soft Dawid Skene actually performs against other methods when we throw some real-world challenges at it.
Awesome. You mentioned before that they tested it on MNIST, CIFAR 10 and 100, and even ImageNet. Did they compare it against any other ensemble methods?
Oh yeah, they did. So they tested it against a couple of classic methods that have been around for a while. Dawid Skene, DS, and Bayesian classifier combination, BCC. Both of these are actually borrowed from Crowdsourcing Research, which is kind of cool. But the interesting thing is both of those only use the predicted class, what we call hard labels, whereas SDS uses those soft labels, the probabilities. And that makes a big difference when it comes to calibration.
So by using those probabilities, those soft labels, SDS is able to squeeze out even more information about how uncertain the model is, which is what leads to better calibrated predictions.
Exactly. They also compared SDS against probabilistic ensembling, or PE, which actually has a bit of an advantage because it uses the training data to help build the ensemble.
So it's kind of like PE is cheating a little bit then.
Yeah, you could say that. But even with that advantage, SDS still managed to do really well in terms of accuracy and, in a lot of cases, even outperformed PE when it came to calibration.
Impressive. So let's break down the results a bit. What happened on MNIST?
So for MNIST, they introduced some distribution shift by rotating the images in the validation set.
Yeah.
And what they found was pretty interesting. In terms of accuracy, all the methods did pretty similarly. But when it came to calibration, SDS was the clear winner. It was better than DS, BCC, and even just the standard ensemble averaging.
So even with a data set like MNIST, which is kind of simple, SDS still shows that it's really good at improving calibration, especially when we're dealing with this distribution shift problem.
Right. And they saw this same pattern when they moved to the harder data sets, like CIFAR 10 and CIFAR 100. They tested it with all sorts of corruptions, blur, noise, even simulated weather effects. And SDS consistently had better calibration across the board.
Or weather effects. That's really cool. So they were basically trying to simulate like different weather conditions to see how well the model would perform in new situations?
Yeah, exactly. And SDS was super robust in those cases.
Which makes sense because it's always adapting, figuring out which models to trust based on the data it's seeing.
Totally. And the fact that it can do all this without needing any labels is really impressive. They actually found that SDS was especially good at something called out-of-distribution detection.
So like knowing when an image is from a completely different data set than what the models were trained on.
Exactly. They created these mixed data sets with both in-distribution and out-of-distribution examples, and they found that SDS was consistently better than PE and EA in terms of AROC, which is how you measure how good a model is at detecting things that are out of distribution.
So SDS isn't just more accurate and better calibrated, it's also better at knowing when it doesn't know something. That's going to be really important for any AI system that's going to be used in the real world.
Oh yeah, absolutely. It really shows you how important it is to account for uncertainty and to be smart about how you combine the predictions from different models.
So we've seen how SDS does on MNIST, CIFAR 10, and CIFAR 100. But what about ImageNet? That's like the big leagues of image classification.
Oh, for sure. And even on ImageNet, SDS did a really good job. They couldn't run PE on ImageNet because of memory issues, but they found that SDS was still better than just ensemble averaging when it came to calibration for most of the corruptions they tested.
So even when you throw the hardest image classification data set at it, SDS can still make our models more reliable? That's amazing.
It really shows how robust and scalable this method is. And another really interesting thing they found was that SDS did well even when the models in the ensemble were kind of similar to each other.
Wouldn't that kind of go against one of the assumptions that SDS is based on, like that the models are supposed to be independent? If the models are too similar, wouldn't their mistakes be correlated?
Yeah, in theory, it could. But the authors actually point out that when the models are similar, that's actually one of the hardest cases for SDS. So the fact that it still works well in those situations is even more impressive. It suggests that if you have an ensemble with even more diverse models, you could potentially get even bigger improvements.
So if you have models that are trained on different data, different architectures, or just have different strengths and weaknesses, SDS could be even more effective. It's like putting together a dream team of experts, each with their own unique skills.
Exactly. And I think that opens up a lot of really exciting possibilities for future research in this area.
It makes you wonder, like, how you could combine SDS with other ensemble techniques, like bagging or boosting, to push the performance even further. But before we get too carried away, are there any limitations or potential downsides to this method that we should be aware of?
Yeah, that's a good question. Like any method, SDS does have its limitations. One thing to keep in mind is that it does rely on this assumption of conditional independence between the models. Basically, what that means is that the mistakes one model makes shouldn't be related to the mistakes another model makes.
We touched on that a little earlier, but what does that mean in a practical sense?
So it means that if you want SDS to work well, you need to have some diversity in your ensemble. If all the models are basically clones of each other, SDS might not be as effective. It's kind of like having a group of experts. You want to have different perspectives and experiences, not just everyone agreeing with each other all the time.
So if you have an ensemble where all the models are basically saying the same thing, SDS might not be the best way to go.
Right. And another potential limitation is the computational cost.
Ah, yes, the classic trade-off between performance and efficiency.
Exactly. SDS does require more computation compared to just averaging, especially if you have a large ensemble or a complex data set.
They did mention in the paper that they didn't try to optimize their implementation for speed, so maybe there's still some room for improvement there.
Oh yeah, definitely. And with all the advances we're seeing in hardware and software, that computational cost might become less of an issue in the future anyway.
Here's hoping. So we've got a few things to watch out for, but overall, it seems like the potential benefits of SDS, especially when we're dealing with distribution shift or out of distribution data, really outweigh the drawbacks.
I think that's a fair assessment. It's a really powerful tool that can significantly improve the reliability of deep learning models, especially in those challenging real-world situations.
So I think we've done a good job of breaking down the results and comparing Soft Dawid Skene to some of the other ensembling methods out there. But before we wrap things up, I want to get your final thoughts. What are the big takeaways for our viewers, the people out there who are building the future of AI? All right, so as we wrap up our deep dive into SDS, what are the big takeaways here for our viewers who are building the future of AI?
Well, I think this paper really shows us that just averaging predictions together isn't always the best way to work with ensembles.
Yeah, it's about working smarter, not harder, right? We got to figure out how to really combine those predictions in a smart way.
Exactly. And SDS gives us this really elegant way to do that. And it's not just like a theory, it actually works. Those experiments show that it really can give you better accuracy and calibration both.
And that's especially true when you're working with real-world data, which, let's face it, never really follows the rules perfectly.
Right. SDS is like that friend who can handle anything you throw at them. Always adapting, always figuring out who to trust and how to adjust their approach.
And speaking of context, I'm kind of curious how SDS fits into the whole world of ensemble learning. There are so many different techniques out there like bagging, boosting, stacking, even Bayesian model averaging. Yeah. Where does SDS fit in with all of that?
That's a great question. So SDS is part of this family of methods called weighted aggregation. It's all about giving different weights to the predictions from different models based on how much we think we can trust each one.
Which makes a lot of sense, right? Especially when you have models that have different strengths and weaknesses. It's like putting together a team of specialists where each one has their own unique skills.
Yeah, that's the idea. And what makes SDS so cool is that it can actually learn these weights on its own from the data without needing any labeled examples. That's a huge advantage in the real world.
So it's like this self-organizing team that just figures out the best way to work together.
Exactly. And because it learns on its own, SDS works really well in situations where labeled data is hard to come by or really expensive, which happens a lot in real-world AI.
So it's really robust and flexible. But we also talked about some limitations, right? Like that assumption about the models being independent of each other.
Right. And that's definitely something to keep in mind. If the models in your ensemble are too similar, SDS might not be as effective. Like it's kind of like having a room full of people who all agree on everything. You need some different perspectives in there to get a more accurate picture.
Yeah, you need that diversity of thought.
Exactly. And then there's also the computational cost, which is another thing to consider.
The age-old struggle between performance and efficiency, right?
For sure. SDS does require a bit more computing power compared to just averaging, especially when you're working with a big ensemble or a really complex data set.
But hey, maybe in the future, as our hardware and software gets even better, that won't be such a big deal.
I hope so.
So it seems like we've got a few things to watch out for, but overall, the benefits of SDS, especially for dealing with distribution shift and out of distribution data, are pretty impressive.
I agree. It's a really powerful new tool that can make our deep learning models much more reliable, especially in those tricky real-world situations.
Well, I think we've covered a lot of ground today. We've really explored SDS and how it compares to other ensemble methods. But before we sign off, any final words of wisdom for our viewers out there who are pushing the boundaries of AI?
I think the biggest takeaway here is that we're always learning, always innovating. And methods like SDS show us that we can keep improving how we build and use AI systems.
It's all about pushing those boundaries, finding new and better ways to make AI more powerful, more reliable, and ultimately more beneficial for everyone.
Absolutely. And I think that's what makes this field so exciting. There's always something new to discover, always a new challenge to tackle.
It's been a fantastic deep dive today. Thanks so much for sharing your expertise with us.
It's been a pleasure.
And to our viewers out there, keep exploring, keep learning, and keep pushing those boundaries. We'll see you in the next episode of AI Paper Podcasts.